Excellent. So yesterday we did kind of the introduction with what we called neural nets or ANNs, various names I think Jim told you. And the idea here was that we had sort of some numerical data of some sort that we could present in a tabular fashion, and we were using it to estimate or classify some of the quantity. And for that we used a neural net and wrote some stuff, went over that. So what we're doing on today is possibly slightly more applicable to a lot of climate science, which is CNNs, so convolutional neural networks. And these are sort of used to process image data or image-like data, which we'll come on to discuss a little bit more in the application session after the break. But the idea of this is that sort of if you were to represent an image as a tabular set of numbers, it's much more complicated to do so, and there's a lot more information there. So what we have are the convolutional neural networks. So some of the advantages of these is that with each layer, because of the way they're structured, there's far fewer parameters than if you tried to do this with a conventional neural net, as we were looking at yesterday. And the way this is achieved is by passing a filter over your image before you start to feed it into the neural net to sort of pre-process it. And so a couple of other points. So when we're looking at this, because we're kind of passing a filter over and looking at things, the way convolutional neural nets are recognizing things it doesn't matter sort of where something is in our image. So in these examples here, sort of if we're recognizing a cat, the cat's in lots of different locations, lots of different sizes, we're sort of learning to recognize a pattern. However, because they're recognizing patterns the way they've learnt it, if the cat is always in an upright orientation, it will have learnt to recognize that. So if you then feed it a cat rotated on its side, it may not be able to do this. But we can handle this with what we call data augmentation, so which is where rather than training on cat images that are always the correct way up, we feed it a random assortment of rotations. So, yep.
It's the fact that they're not rotational invariant. So it's related to the fact that in the convolutional networks, the stencils are square and not circles, or will it even happen if you were able to use circles?
So I think you mean sort of the filter that you pass over. Yeah. So I think it's more to do with the fact that if your training data is passed always in one orientation, so if you were say you were training something to recognize human faces, if it's always looking at a face that's the correct way up, because it's difficult to say exactly how a neural net is working, exactly what it's looking at, because they will they will recognize features in a very different way to how a human brain recognizes features to work out what something is. It's to do with sort of, it will learn to recognize features of something that's the right way up, because once you feed it images that are rotated to different orientations, even though you still pass a square stencil over it, it will then usually work. So I don't know if Jim wants to talk about stencils and bits. Yeah. So the idea of this is, if we start with sort of 1D, cool. So suppose we have kind of a 1D image which is made up of sort of these pixels here. what we do is we take what we call a kernel, which is kind of just a 3-pixel stencil. And the idea is that we slide this kernel along our image and sort of take some computation of the combination of all the pixels that lie under that kernel. So often you say here dot product with some bias. And so you can see that by sort of taking those 1, 2, 3, 4, 5, 6, you've reduced your sort of larger image down to a vector of length 6, which will have some form of information about the groups of pixels encoded within it. And then once you've done that, you can then pass that into a neural net, as we did yesterday, and sort of these kernel snapshots become your input features, as it were. Dominic?
Is there any standard advice about how you handle the boundaries, or is it, a little bit problem dependent? Here you're sort of ignoring the boundaries, right? So there's a bit of bias.
Do you mean?
The pixels at the far edge only get visited. They only contribute to one feature, whereas all the others contribute to 3 features. So.
Yeah.
Usually with random noise, pad the image so that.
Yeah.
But yeah, that basically is what people do.
Okay.
Or you could, if you had sort of, say you were doing something with periodic boundaries, you could have sort of a stencil that slides beyond the end back to the start.
So you do the normal things that you would do for other stencil computations, but it's kind of domain specific, what you want the effect to be.
Yeah, and I think that we'll come on to a bit this afternoon, is so much of machine learning is important about thinking about what data you have and thinking about what you apply to it is sensible, rather than just going around with your 5-layer convolutional neural net and whacking any image you can get your hands on.
Right, so it was a bit like yesterday when we were talking about the penguins, like that relied on us knowing things about the real world and knowing about penguins from observation first.
Yeah,
and being and you're doing some analysis of the existing data, essentially.
Yeah, and like Jim said, if you suppose each penguin species was located on a particular island, if you'd fed island into that model, the model would have just learnt to recognise what island you've given it, rather than inferring any information on physical characteristics of the actual penguins. Cool. So then if you've got, obviously these are all sort of single numbers. If you've got, say, an RGB image, then each pixel is going to have 3 numbers, red, green, blue. And all you do with this is we have kind of a multi-channel kernel for red, green, blue, pass it over in the same way. And there's a lot more information on this in the sort of conv1d docs on Pytorch. As Jim said yesterday, they're very good. So moving to 2D is, pretty much the same. Like with lots of physics maths classes, we start simple and then just extend. So here you now have a 2D image, you pass a 2D kernel over it, and you just slide along in the same way. And there's good documentation on Torch conv2d. Is it? Yeah.
And you assume that each image has the same resolution?
Yes. Can you assume, or do you assume?
Yeah, maybe you can have images maybe which have a coarse resolution and one which are high resolution. And
Sorry, could we do this with the mic? Sorry.
Then you have data with different lengths or something like that?
So for this, you will assume that everything is, because you need to match up the features. Again, if you had images of different resolution, you would have to deal with that with some kind of preconditioning before you pass them into your data set. I don't know if you have experience.
So I normally work in medical image analysis, and the first standardization step you do is to standardize the resolution. But people do train multiple models on multi-resolutions. Usually it impairs the performance, because I'm going to use a very specific example, but say you have a model that's detecting nuclei in an image, then basically it becomes attuned to the size the nuclei are when they're first presented to the model. And then if you vary the resolution, then obviously that size is widely distributed. It doesn't really make sense to do it unless you have a really niche reason.
Yeah.
You might.
How do I do this on a...
Yeah, F6, isn't it?
I think you're at the end anyway, to be honest.
So a bit like we've said already, when you have a convolutional neural net, what you're doing is sort of taking these, sliding this stencil or this kernel along your image, and there's sort of a series of layers, and this is what sort of performs what we call feature extraction. So if you think about how we would recognize different animals, you might look at a cat and see that it's got 4 legs and a tail, and you might look at a dog and see it's got 4 legs and a tail, and sort of then you might look more closely and begin to sort of work out, is this a cat, is this a dog? It's nice to sort of think that CNNs are doing the same thing, but as much as people have been able to probe into them, the features that they're extracting are sort of usually very, very abstract. So you'll run the stencil over, do some feature extraction, and these features that this layer has pulled out then get fed into this fully connected net, like we saw yesterday, and then fed ahead to do either classification or regression, as we've already done.
Can I just say that the feature extractor part is often called an encoder, but basically the purpose is it finds a representation of the input data that is then conducive to either classification or regression. So like you can think of it as it's just finding an abstract representation of an image, which hopefully contains like salient features, and then those salient features are used to make your prediction. So it's like basically like a 2-stage thing.
Cool. So are there any questions on CNNs and that sort of thing? Nope. Cool. In that case, we'll go on to the exercises. So it's the same process as yesterday. You'll see there's I think, exercise 3 and 4 in the Jupyter Notebook. So if you all want to boot that up, and we can get started. And do you want to use your laptop?
Preferably, but I don't mind. I should also apologise to everybody for being late. My bicycle chain snapped halfway here, which is why I'm covered in oil. I promise it's nothing to do with the pub last night. Oh, excuse me. I actually don't know if I'll need the internet, but I may as well do it.
Yep. So in... just where are the exercises? So in the Jupyter Notebook that we had yesterday, if you go into the exercises folder where you found the penguins were exercise 1 and 2, and so today the convolutional neural networks will be 3 and 4.
So I think given that yesterday we only managed to do one exercise, we're just going to focus on one exercise today. And people last night said they would rather do classification than regression again. I don't know if that's the general consensus, but unless anyone strongly objects, we're going to do classification again. And we're going to classify handwritten digits in the MNIST dataset. So the exercise is the one I'm just about to open, which is 0,
Oh, can you make the font bigger, please?
That's what I did.
I think, yeah, okay.
Can everyone see that? Is that okay? Yeah. Okay, cool. Oops. Okay, cool. So, does anyone no idea what the MNIST dataset is? Has anyone never used it before? Yeah, okay. So basically, it's a giant dataset of 70,000 handwritten digits between 0 and 9. It was collected by NIST, which is basically the American equivalent of NPL, which we have here at National Physical Laboratories. And it's basically super simple. It's just they gave people a grid of 100 numbers and asked them to do 0 through 9 on every row, and then they got 70,000, which is pretty impressive. So the first thing we need to do is get access to the MNIST data, and fortunately that's been made exceptionally easy for us by Torch Vision, because I'll just quickly show you the... So basically Torch Vision has a bunch of publicly available data sets packaged up in a very sensible way. So if you want to like play around with a given model architecture and benchmark it on different data sets, you can basically come here, pick one from the menu of data sets, and then play around. I find this really good if I'm working on like a domain-specific problem and I think something's wrong, then I sometimes will go and grab like a publicly available data set just to give myself a sanity check that like my pipeline works. So like, you know, for example, you might have a problem with like ground truth accuracy and your data set might be poor, so you can see, is my model really bad or are my labels really bad? So I can go and take MNIST or something that I trust and just like sanity check. So basically we need to tell Torch Vision where it's going to save the MNIST data. I recommend everyone just does exactly what I've done here and say MNIST root, and then you can just delete it when you're done. So yeah, basically to access datasets, all we have to do is say from torchvision.datasets import my dataset of choice. So you need to give it 2 arguments, where you want it to save the data, and you have to say download equals true. If you don't say download equals true, it will try and find the cached dataset in this location and an error. So yeah, basically, does everyone want to download? Does everyone? Yeah, it's not. I don't actually know how big the dataset is, but I don't think it's that big. So basically, yesterday we said we need 4 things, right? We need a dataset, a model, a loss function, and an optimization procedure. So we're actually going to do this step for step. So the first thing we can do is, where have I written it? Actually, I've jumped ahead too fast, excuse me. So first of all, now that we've got the MNIST dataset, I guess the first natural thing to do is look at the data and say, how are they given to us? So we can just iterate over it by saying for, let's just say image, target. So this dataset contains, like I said, 70,000 items, and we don't want to print 70,000 items, we only just want to print a few. So let's just say we can print, just bear with me a moment, so we can say image, target, and does everyone know about the Python function enumerate? Actually, I don't want to do enumerate there, I want to do zip. So this basically will only give us 5 input target pairs rather than the full 70,000, which would be a really stupid thing to print out. So if we print just image and target, you can see that the first printout is a pillow image object, and then the second printout is just an integer. Funnily enough, that integer tells you what number has been written in the picture.
Is it worth also changing download to false now that you've downloaded the dataset?
I mean, it won't duplicate, but...
But it is just in case anyone reruns that cell.
Yeah, so like, if you put download equals true, it checks for the cache data, and if it's there, it doesn't download it. So because we're dealing with images, again, the most sensible thing you can do is plot them. So let's just quickly see what our data look like. You can plot them however you like. I have a tendency to always use matplotlib. Let's see, 10 by 2. Okay, so then I'm going to add another thing to our loop called axis. And then inside the zip, I'm going to say axes.ravel. So axes is actually just a NumPy array of individual plots. And NumPy arrays have this method ravel, which basically iterates through each element in it. So rather than saying axes square brackets 0, axes square brackets 1, it's like a bit more elegant to just use this iterator. So now we can say axis.imshow, which is a function for showing image, and then we get our 5 images in a grid of subplots. And then another relatively sensible thing we can do is say axis.set title, and then set the title just to be the target. So we can make sure this target is a 5, the image is clearly a 5, and a 0, and so on. Right, so again, nothing fancy, we just plotted images and looked at the labels, but it also tells us how the data are given to us and how the targets are encoded. Yeah, so does everyone want to get to this point, and then we'll go ahead? I'll get out of your way, Paul. Sorry, I don't know if I should have used enumerate rather than zip, if there's a stop argument to enumerate, but it's really matters.
Presumably, if you're only pass it range 5, it truncates
Yeah,
the
it
data
does.
set at 5.
Yeah, otherwise the plot would be broken.
Yeah. But as in, there's no danger of it getting stuck in a big loop.
Yeah. So does everyone have the data plotted? Does anyone not have the data plotted and doesn't want me to go ahead? Okay, cool. So yesterday, you remember, I hope, that we looked at the raw data, realized it was in a format that was not yet appropriate to be fed to a neural network. So like step 1 is, can we convert the data to tensors? So the way that you can convert an image object to tensors has been made unbelievably easy, again, by Torch Vision, because they provide lots of functionality for us. So if we go to the documentation for Torch Vision's transforms, is this it? So in here they have a thing called toTensor, which I can't spell. So if we look at the documentation for this object, it converts a pillow image or a NumPy array to a tensor, and it scales the values. So if we have an 8-bit unsigned integer image that goes between 0 and 255, this function will create it'll basically convert it to a float and then rescale it so that the maximum value is 1 and the minimum value is 0. So basically it normalizes. And one thing which you may notice is conventionally, I don't know how well you can see this, when you have a RGB image, the dimensionality is height by width by number of channels, where number of channels is like the red, the green, and the blue channel. But in Pytorch, just to mess with everyone's head, they put the channel dimension first. So an RGB image has shape like 3 by height by width, and which I presume there are good memory reasons for doing that I don't understand, but I imagine it's a good C++ thing at some point somewhere, but I don't know why.
Yeah, I would guess if you're sliding the stencil, it will be to make something useful concurrent in the memory.
Let's presume they didn't do it just to be mean, and there's a good reason for it. So I've written a function to produce some transforms initially here, and the function is basically get image transforms. It takes an argument training because we're going to augment our data, and we only want to augment our data when we're training. So it does basically what we did yesterday. It puts a bunch of callable functions inside the compose object, and then if training is true, we might like to stick in some transforms here which augment the data. But we'll come back and do this like in a more interactive way. The only other thing I've done here is I have this lambda function called x.repeat, because we're going to use a model that wants RGB images, and MNIST is grayscale. So all I do is repeat the tensor across the color dimension. And then like a fundamental basic of color theory is if the R, the G, and the B pixels are equal, you're on grayscale anyway. So it actually doesn't matter if you broadcast a grayscale image across the RGB dimensions, as long as each pixel in each channel contains like just one value, essentially. No, all of the channels only contain one value.
Second question.
Oh, sorry, yeah. Yeah, so if you have a, well, actually, let's just do a quick example in the terminal. So if I have an image on grayscale, let's just plot one as an example. I don't know why that takes so long. So let's say we'll just call it grey equals torch rand. So we have a random image, just an image of random noise on grayscale, right? And then if I say, if I plot this image, right, it's on grayscale, but Matplotlib uses the default color map, which makes it look, I should have got rid of that. So let's just say CMap equals, this always causes me trouble because they say greys with an A and not an E. Oh, did he do it with an E?
Lower.
I'm confused. No, it's not. It's, the convention is capital. Greys,
Yeah, I think
G-R-E.
yeah, it's lowercase g.
I can see the, this is, yeah, I want this.
Right.
Yeah. Right, so we got, whoa, a blank image. What? Did I make that? Oh yeah, maybe. What? Image? What did I call it? Grey. It shouldn't be that standardized. Okay, I'm doing a very bad job of this, but let's just be paranoid and say the color scale might be being rescaled or something stupid. Yeah, so right, we have the grey image, right, which took a stupidly long time to produce. So in Pytorch convention, the grayscale image should actually have a channel dimension. So let's just say, sorry, just bear with me 1 second and then I'll explain why I've done this. Okay, so if we look at the shape, grey.shape, oops. So it's basically got one color channel, which is why this dimension is 1, and then 10 by 10. But if we instead plot, this is going to error, but it's also a good illustration. So we can say grey.repeat, like I literally have done in the notebook, and then we want to repeat 3 times across the channel dimension, and then we don't want to repeat. So this is going to shout at me because the channel dimension is at index 0, and most conventionally it should be at 1, so it's going to say invalid shape for image data. So we just have to reorder the dimensions, which you can do using Pytorch's permute function. So now, why? I really hate this thing now for doing this to me. This is a really, really long-winded way of making a super simple point. But basically now this is a 3D tensor, right? And because we've copied it in the RG and B channels, and because the R value, the G values, and the B values are all the same, it's grayscale. Yeah, I don't know why that was more elaborate than it needed to be, but so I've forgotten how I've organized this. Let me just remind myself. So yeah, step 1 is let's make our training and validation sets as we did before. So like I'll instantiate like the training set, then you can do the validation. And then we'll come back here and choose what sort of data augmentation we want to stick in this get transforms function. And then we'll go from there. I realize I've actually done all of this for you now that I've said it. It's super helpful. Okay, so let's just go through what I've done here, right? So I've instantiated the training set, so just by calling the MNIST, or instantiating the MNIST class, and then saying train equals true. So yesterday I prepared like a custom data set for you, but we don't need to do that today because Torch Vision's done it for us. So all we have to do is supply the transforms to map between a pillow image and a tensor, which is the getImageTransforms function we used just a minute ago. And then the target transforms, so basically how do we go between our index encoding to one-hot encoded vectors. And then all I've done is plot 5 images. And I've done this same permute thing as well. So the images have shape C by H by W, but I'm reordering it by saying putting the 0th dimension last so that it conforms to the standard RGB image shape. And then Matplotlib won't yell at us. Does anyone not get what's going on? Have I gone too fast?
You just repeat it.
Yeah, so basically, we've instantiated the training set, right, and the validation set. We've then grabbed 5 images from the training set by doing this for loop here. So I iterate over my 5 subplots, which caps the maximum range of the loop. I get an image and a target from the training set just by saying train set, square brackets, index. And then I plot the image, and I do this little permute trick to make sure the dimensions are correct. And let's just make sure it runs. So yeah, you can see we have grayscale images. One thing we could also do is, you know the title says tensor 5. Like, we don't really need it to be a tensor, we actually just care about the number, so we could say target.item when we set the title, and then it just like gives us the value and drops all the other tensor stuff. It doesn't matter, but just slightly cleaner. Okay, cool, so now, as Jack told you, CNNs are translationally invariant, which basically means they don't care where the thing of interest is in the image, but they're not rotationally invariant. So if we train this model, it might learn to identify ones because it detects like hot vertical edges. Took me too long to figure that out. But if we don't like endow the data with like rotations and other randomness, the model has no incentive to learn like what happens if I get a 1 that's fallen on its side, because you've never trained it to do that task. So the stochastic gradient descent, basically there is no incentive whatsoever. So basically it would be pretty useless. So the cool thing we can do now is going back to this function and say when we list our transforms to convert between a pillow image and a tensor, we can actually just append more transforms which do the data augmentation steps for us. So now if you want to choose transforms, hang on, let me get to the documentation. So Pytorch has made a whole bunch of image augmentation functions for us, and then given really good demonstrations of how they work. So for example, this is like a form of augmentation, center crop. If you look at it, it'll just randomly crops the image to like only include a certain size square in the middle. What else do we have? Color jitter, so then it just randomly augments the brightness, contrast, saturation, and hue. So basically it noises the color of the image. And then there's like basically a whole menu that I won't go through, but there are tons of like fun things you can do to mess with images just to augment them. So what I think, like for example, there's grayscale and random grayscale, so you can randomly grayscale inputs, stuff like that. So the minimum augmentations I would suggest we do here are color jittering and random rotations. So we can do color jittering first just by importing the color jitter object from torchvision.transforms.
And the analog from yesterday was sort of when we added the layer that occasionally dropped features out.
Yeah, it's really easy to augment images. It's kind of harder to augment in the form that we did yesterday. Okay, so now we want to add color jittering to our pipeline of transforms. So literally all we have to do is append an instantiated color jitter object. So let's say we want to, so this basically, it augments between uniform random noise between 1 plus or minus the value you give. So if you want to go between like 95% and 105%, you would pass 0.05. Let's say 10%, why not? And again, these are all things you can tune, right, to satisfy performance. So there's no rule about, oh, you shouldn't go beyond a certain value. It's literally just performance driven. What else do we have? Brightness, and I really don't like that this is going to go over into another line, but. So does everyone get what I've done here? Like I can drop this pass now. So all I've done is taken out our list of things that we're going to call when we put an image to them and added color jittering. And then the other thing I suggest to add are random rotations, because CNNs are not rotationally invariant. And and then basically the only thing you need to know for random rotation is it will randomly rotate the image to plus or minus the number of degrees you give. So if you want to do full 360 degree rotation, you can just pass 180 because it does plus or minus 180, so you don't need to pass 360. Yeah?
Does the rotation not matter for the digit? Like if you rotate a 6, you get a 9.
That's a good point. I don't know, but you could try and look for that as like a test when you're evaluating your model and say objective, like, yeah, that's quite, I don't know. I guess it depends. Oh yeah, sorry, so someone asked if we rotate 180 degrees, might the model confuse 6s and 9s? Maybe it will, I don't know. But those are the kinds of questions you should ask when you're evaluating a model, right? You shouldn't just look at the overall accuracy, you should think what are the edge cases and the special places that might go wrong, because that's where you find interesting stuff that makes you rethink.
So if you ran your validation, you could, rather than sort of looking at the accuracy of as one metric, you could separate by individual digits, and you might expect to see sort of a drop in accuracy of 6s and 9s.
Like, generally speaking, accuracy is a really bad metric that everyone wants to use because it's simple. But if you think about, if I have a data set that's got 99 negatives and then like 1 positive, then a moron model that just says no all the time will get 99% accuracy. So you should also think about like true positive rates and false positive rates and be more objective. Accuracy in this case is okay because we have a balanced population of each class. So like, but it may well be that when you evaluate the performance, we underperform on 6s and 9s that are rotated. So basically you have to be paranoid and check these things. Obviously in this case it doesn't matter if we get it wrong because it's just a demo. But yeah, if you're doing something important, then you should check. Okay, so I'm just going to comment out the random rotation quickly so we can look at the plots again with and without the various augmentations we've added. So this is with color jittering. And to be honest, it's not done very much. So I'm going to up the strength. I'm slightly concerned now that we're not getting like a very exciting. Okay, let me just check that this is definitely working by encoding the rotation. Yeah, so I don't know why the color jitter has been so weak. Anyway, it's not worth getting obsessed by. Let's just heavily augment brightness by a crazy amount to see if it works. Yeah, okay, so maybe I've chosen to weaken augmentation because it wasn't visually perceptible, but we'll leave it like as it was for now. So basically, if everyone now adds their augmentations and reruns this cell, do they now get like randomly messed up data and not the original? Okay. If you want, you can go and look at the menu of possible augmentations and Torch Vision's documentation and pick all the ones you think are fun. Like, you don't have to just use the 2 ones I've used. You can like randomly blur the images, you can add Gaussian noise, like you can do like split the image up into small tiles and reorganize them so that like you mess it up, basically mess it up in every way you can think. But yeah, there's no point in going through all the possible augmentations because the documentation has really good demos of all of them, so you can just go and look and choose. Yeah. Oh wait, sorry, we have to do this so you can hear on Teams.
I assume that these transformations don't extend the size of the data set, so they just transform each member?
Yeah, so sometimes, like when you randomly rotate a patch of the, like we have square images, right? So if we rotate by 45 degrees, then some data is going to go outside the image dimensions, and we're going to get like basically black spots where it used to be, if that makes sense. So you can like, basically sometimes people will artificially pad the image before they do the rotation, or they choose like an image that's like the square root of 2 bigger than they need, rotate it, and then center crop to the actual training size they want. But you do have to think about like these things.
Well, what I was actually referring to is that the number of digits in this data set is equal to the number of digits or images in the original data set.
I'm not sure what you mean.
As in,
Is
you're
that
not
the case? Or
like you're not getting, when you rotate, you don't get the original and the rotation.
No,
you just
that's
get
the rotated.
the rotated image.
Yeah.
if I want that, so if I want the original set and set to which some perturbations have been applied, do you just do the repeat? Or is there
So
a
norm
more fancy way of doing that?
Yeah, so normally normally you don't care when it's your training set, right? But you don't do these augmentations in the validation set because then you want like regularly ordered things to validate on. If I wanted to like have a augmented and unaugmented version of each image, I would probably instantiate 2 data loaders, and then give one of them the training transforms and give one of them the validation transforms, and then you would have like basically a like for like of each, which is not really that elegant, but I'm struggling to think why we might do that, unless you just want to visualize the difference. Do you have a reason in mind for?
Because you would have a bigger training set. If you
Yeah, but like, if you think about this right now, we've got 60,000 images, and we've got like a virtually infinite possible number of augmentations. So the probability that the model is going to see the same input twice is effectively 0. One thing you can do is like, there's a random apply thing that says like, I'm going to give you these 3 augmentations, but I only want you to apply them like 25% of the time. So you mix it up with augmented and unaugmented training data, but yeah. You could do what you said as well. In the case of this really simple data set, it's not going to matter, but there was a question behind you. Will you pass the mic back?
I was just going to say that during our guided team challenge in our master's year, we had some like satellite images, but we didn't have enough data of like particular features like sea ice boundaries in these images. So we augmented some of them and then added them on to what the data that we already had to like have extra training data.
Yeah, so that is effectively what we're doing here, right? Is we're trying to artificially increase the size of our training set to capture things we don't have, such as rotated images in this case. It's not universally true, but I always find that the more heavily you augment data, the worse performance will be on small data sets, and in big data sets, it makes so much more sense. Yeah, but again, it's all performance driven. You might heavily augment a small data set and do really well just by chance because your data set was conducive to whatever you did. So I hate the fact that there are like a lack of clear rules about what you should and shouldn't do like in terms of this stuff, but it really is like, you know, pick something, try it, evaluate it, and decide if you're happy. Okay, so everyone now has perturbed images on their screen. Yeah? Okay, so then, just like we did yesterday, we created data sets which deal with individual XY pairs. Now we want to wrap our data sets in data loaders so that it can prepare them in mini batches and then take care of the random shuffling and other stuff. So because the MNIST images are really small, I've forgotten what their dimensionality is, actually. Let's just print it. I think it's 9 by 9, but I don't know why. 28 by 28. Okay, so the images aren't particularly big, so we probably don't need to worry about memory. So I'm just arbitrarily choosing a batch size of 64 because I'm strange and find powers of 2 appealing. But basically, we're going to create our training and validation loaders as we did yesterday. So all we do is wrap the training data set. Train set in a data loader. We tell it the batch size. Because this is our training set, you don't have to, but I'm going to randomly shuffle it at the end of each epoch so that the order in which the inputs are supplied is different every time. So I'm not going to do it here because it doesn't matter, right? But if we were dealing with really, really big images, we might like to add the num workers argument, and then this would make the data loader load mini batches in parallel. So just by increasing the number of workers doesn't always mean you get better performance, right? Because it really depends what computer you're on. Like, if you have a really rubbish old hard drive, there's no point in trying to load like with 24 workers because it just doesn't, it makes no sense. And then we'll do the same thing to make a valid loader. Whoops. And the shuffle argument is by default false, but I like to write it just as a sanity check because I'm worried that one day they'll change it and then something will go wrong. I think it's better to be explicit when you don't want to mess up the training and validation splits. Okay, let's see if this runs. Okay, so now let's just iterate. How should we do it? Whoops. Actually, I don't want to do this. Excuse me. Actually, I do. So I'm just going to iterate over 5 mini batches so we can print out the shapes and make sure they're what we expect. And we'll do it with the train loader. So let's just print out the shape of one batch. So you see that the shape is 64 by 3 by 28 by 28, right? So 64 is the batch size, and then 3 is the number of color channels, and then the 28 and 28 are the height and width of the image. Okay? Some people get confused by this. It suddenly becomes 4D and they think, oh my goodness, what's going on? And another thing we should check is the shape of the target. Oops. Oh, damn. Okay, so I am very stupid and forgot to supply the target transforms. I just converted the number to a tensor, which is not what we want to do, right? We have to do the thing we did yesterday. Sorry. So we import the identity matrix. Then we return
the thing we did yesterday being converting it to a unit vector that will always be length 1 with one element representing the number.
I'll print it in a minute just to make sure. So can everyone go and modify this line to look like this now? And the and the target as tensor function.
Can you push it up a bit?
Oh, sorry. Yeah, so it's just from torch import I. Sorry, we really could have like chosen a better setup to visualize this stuff. Does everyone more or less have this now? It's pretty important. If you don't, we should wait. I'm concerned that some of you look actually stressed. Okay.
It is a fairly good way to sober up, I guess.
Yeah, so let's just rerun this. So just to do a quick sanity check, we got an error. A tensor with 10 elements cannot be converted to a scalar. Did I just tell everyone to copy me and I've done it wrong?
I think so. If you get 5 white squares, that's what I've got.
What is the function again? The target transforms. I target in. Oh, right. I haven't done it wrong, I'm just stupid. Yeah, when I put target.item in the title, it's now yelling at me because we can't, .item only works if you have a 1x1 tensor. So this, if I run it now, it should work. So let's just print the target shape to reassure ourselves. So the target shape should be like just a vector of length 10, okay, which is what we've got. And since that's not much print out, let's just print it. So you can see that the first image, oh god, what is it, 5. So now we have a 1 hot encoded vector with the 1 at element 5, right? So 0, 1, 2, 3, 4, 5. This one's a 1, so let's use it because it's easy to count. So we have the one hot encoded vector 0, 1. Okay? So like the exact same thing we did yesterday. You just have a unit vector whose maximum argument is at the index of the value of the number we have. I'm going to get rid of that printout just because I don't like it. That's disgustingly ugly now, but okay. So let's just add dot argmax to get back to a number. Okay, so now if we go back to our data loaders, we should be getting targets that have the correct shape. Okay, so is that what I expected? I don't think it is. We have another problem. Yeah, so the target shape should be 64 by 10.
You missed an S. It's targets.
Yeah. This is not a good example of how to name variables, is it? Yeah, okay. So we have like 1 unit vector per item in the batch, so it's 64 by 10. I'm really glad you were paying attention because that would have taken me much longer than it should have to figure out. Okay, cool. So I'm just going to get rid of this because there's no point in having a random printout that serves not much purpose. Okay, cool. So now we've dealt with the data angle, which is like always the most like cumbersome thing to set up. Now all I have to do is choose a model, choose a loss function, and then choose an optimizer, which are all relatively quick things to do. So for this exercise, I'm proposing that we use a commonly used neural network called MobileNet. And the reason I'm recommending MobileNet is because it was designed with running on mobile phones in mind. So I think it will be kind to all of our laptops, which don't have GPUs. But basically, where are we? Torch. If you go to the documentation for torchvision.models, they have sorry, excuse me a minute. Yeah, so if we go to the documentation for Torch Vision's models, they have, once we get by all the rubbish bump, tons of commonly used CNN architectures. And the useful thing they do, for example, if we look at MobileNet, is if you click on it, you can always get to the paper within like 2 clicks to say, you know, how is this model developed if you want to read more about it. And that's true like of ResNet, it's probably the most famous model here. Anyway, so you could in principle use any of these models for this exercise, right? They're all just they're all CNNs designed to work on RGB images, but we're using MobileNet because it's small and makes more sense. So to instantiate a model, okay, there's a couple of things happening here, so let's just do it one bit at a time. Pretend this bit's not here initially. So to instantiate the model, initially all we have to do is say from torchvision.models import the name of my model, and then to instantiate it, just literally this simple, right? One thing that Torch Vision has done, which everyone I've ever worked with capitalizes on without thinking about it, is it's made pre-trained weights available for all of these models. So every model they make available online, they've trained on ImageNet. So even if you're working on a completely different problem that's got nothing to do with images that look like the images in ImageNet, you usually still get better performance if you use that as your initial condition, because it's still learned to like identify abstract features. So it could be like edges or dots or something, right? So, you know, if you had to choose between using a totally random initial condition or something that's been trained on another problem, even if it doesn't make sense in your head, you usually find better performance with the pre-trained initial condition. And the process, or the process, I guess, of using an initial condition from another problem is called transfer learning, which is a much fancier name than it deserves, to be honest. So to supply the pre-trained weights to a model, I do uncomment. You can import the weights from Torch Vision. So for example, we've got from torchvision.models import MobileNet v3 small weights. And then if we run this, it downloads the weights from Pytorch, caches them somewhere, and then endows the model with them. I think this is quite, to be honest, quite ugly to look at. And I can't remember if it works, but I think you can also just pass default as a string like this. And it will download the most up-to-date version of the weights they've released. But that might change. So if you want a really reproducible initial condition, you might like to specify the exact version of the weights, rather than just taking the most up-to-date ones that happen to be online on the day that you ran your code. So if we then print our model, this printout is rather huge and ugly, but there's not much we can do about it. You see, basically, it's got a bunch of 2D convs and batch normalization and then nonlinear activations. So basically, all of the things we used yesterday, but rather than fully connected matrix multiplication, it has convolutionals. I wouldn't try and don't try and look at this and see how do I follow like the path through this function, because it's super complicated and really long. Like if you want to read it, I would suggest you basically do it offline. And read the documentation that explains it. Like the paper, for example, will have a picture that gives you an overview of the architecture, which is way more useful than trying to read this really verbose printout. So does everyone have a model instantiated with pre-trained weights? Yeah? Do you want to use the mic, or like, I'm sorry, I know it's annoying, but your input's not working? What are you trying to import? So, okay. Can you comment out the weights part and try and import the model just to see which line it is? Yeah, you could try that. That's a good starting point. Yeah. Is it possible there's a typo? I mean, we all have the same versions of Torch Vision on our computers, so in principle, something funny is happening. What does it say when it errors?
So it runs the first import, the first line.
Yeah.
It gets to the second one, it says, cannot import name MobileNet v3 small weights from torchvision.models.
Okay. And are you using the right the identical capitalization and stuff on the? Okay, so if you uncomment that line, comment that line and then just write weights equals default in block capitals when you instantiate the model, does it then download pre-trained weights for you? Okay, cool. We can try and figure out why that is, like, it's not important to do it right now, but that is weird. Okay, so has everyone now got this model with the weights? Right, amazing. Okay, so we have one tiny annoying problem we have to address before the model's ready to use. Geez Louise, this is so much. So if we look at the final layer of the model and the classifier, we see it's got 1,000 output features. Right, that's because there's 1,000 classes in the ImageNet dataset, and that's what this model was developed and benchmarked on. But we have 10 output classes because we have 10 digits. So we basically need to overload the final linear layer with one whose dimensions are appropriate to our problem. So it's, I mean, I've done it in here, but all we have to do is say model.classifier3. So why have we done that? So if we type model.classifier, we get this bit. And then the final linear layer has index 3, right? So model.classifier item 3, and then we'd replace it with a new linear layer. So we keep the number of input features by reading them from the existing object. So we just say, like, the layer we're replacing, use the same input features, but we want 10 output features because we have 10 classes. Oops, what have I done? Yeah, this. And then just to make sure is changed, we can then print model.classifier. So there's no point in printing the full model out. We just want to check the final bit. And we get an error. Spectacular. Has no... Yeah, I'm just a moron, to be honest. Yeah, okay, cool. Thank you. So does everyone have this final layer overloaded? Okay, so now the model's producing outputs that are the correct size. So the final few things we have to do, actually, I'm getting ahead of myself. Right, so because yesterday we trained on a very small data set with a very small model, so there was no advantage to putting the model on the GPU because the training time was like fractions of a second per epoch. But obviously images are bigger, so you might like to put the model onto a GPU. The way people tend to do this is to introduce a global variable called device. And I mean, I don't know if you can see what's happening here, but basically we use this isAvailable function from torch.cuda that tells us if there's a CUDA ready GPU on the machine that the Python can talk to. And if there is, then we'll set the device to CUDA, which means use the GPU. And if it's not available, then CPU. So, for example, let me just print it. I absolutely don't have a CUDA-enabled GPU on this machine, so I get CPU. If anybody's got like a fancy gaming laptop, or maybe or a Dell XPS or something, you might have a NVIDIA GPU. No one? No. Okay. I'm going to use this anyway because it's good to see how you. Okay, so, oh yeah, and sorry, I forgot to say. So to put the model to the device, all you have to do is make use of .2. So this returns a reference to the model, but it also modifies it in place. But I've just put this stupid thing here because I don't want another ginormous printout. So I just suppressed the printout by assigning it to this. But the model basically is moved to whatever device. Okay. Is it everyone roughly okay? Simon gave me in trouble for being too fast yesterday, so I'm going to check. Okay, so, oh yeah, what have I forgotten? Yeah, so we need to also have our loss function and our optimizer. So just exactly as we did yesterday, we use BCE for the loss. For our optimizer, we use Adam. And again, we have to give the optimizer model.parameters and tell it what learning rate to use, which we use set to 10 to the minus 4. Sorry. Has everyone got this? Yeah? Simon? You look horrified. Okay, cool. So we've we've got, what have we done? We've got a model, we've got an optimizer, we've got a loss function, and we've got data. So that's like the 4 basic ingredients are here. So now all we have to do is train and validate. This might feel a bit boring because it's like almost the same thing we did yesterday. So you can see the same thing, train one epoch, we give it a model, a training data loader, an optimizer, and a loss function. I can't remember if I wrote these loops out. Okay, I'm just going to write the training loop, and then maybe you can write the validation loop like we did yesterday. So the first thing we do is iterate over the data loader. So we say for batch, comma, targets, and train loader. And since there was a mistake in the doc string yesterday, I'm just going to check that train loader says train loader, yeah, okay. So the first thing we do is clean out the gradient history that we may or may not have. But I mean, we'll have it after we've done one iteration of this loop. So then the second thing we do is infer. So let's just say pred equals model batch. And we haven't applied an activation function because the default Torch Vision models don't put an activation function in the final layer because it might not be appropriate to the problem you're using. But since we're doing an identical classification type problem to yesterday, we can use softmax, and we do the exact same thing where we apply it across the first dimension. Yeah. Is everyone okay with that? Yeah. Forgotten what we do next. Yeah, loss. So then we calculate the loss, and again, Pytorch convention is that you put the predictions as the first argument. Okay. And then we do backpropagation by typing loss dot backward with parentheses because it's a function. And then the final line is optimizer dot step. Sorry? Oh God, thank you. This is taking me ages to debug. There's one other thing that I haven't done here because I'm stupid and I forgot. But basically, we've put the model, potentially you've just put your model onto the GPU, but the batch and the targets are 32-bit floats that are not on the GPU. So we have to add this line, batch targets with an S equals batch dot to device. And then the same thing, so this is just like assigning variables using a tuple, targets dot to device. So now the device of the input data and the target data will match the device of the models because we're setting them all to the device. Okay? I often forget to do this. One thing I should also actually say is when you're debugging, go and manually set device to CPU because you get much more verbose and helpful printouts. When it's on the GPU, you get almost no helpful printouts, and it can be infuriating to try and debug. It's always worth doing that if you're ever stuck. So does everyone have this loop? Okay, shall we go, do you want to go and write the validation loop? Oops, excuse me. I'm going to do something really bad and just copy and paste this and change stuff. But so remember the difference. Oh, why am I such an idiot? So we don't need an optimizer in the validation loop, but for some reason I've supplied it as an argument. I'm going to delete it actually because it's a bit annoying. Probably because I copy and pasted the code and then forgot to delete it, to be honest.
Blame proofreaders.
Yeah, at least the doc string's right this time, but the arguments are wrong. Okay, so I'm just going to write this slowly, but you don't have to do it at the same time. I really don't like this keyboard. We'll calculate the loss, but temporarily we're not using it, but then we will store it. Threads. Okay, does anyone not have the validation loop yet? We good? Okay, so we haven't extracted any metrics, but we can just do like a one epoch pass of each loop to make sure it works. Invariably, we'll find bugs. Yeah, sorry. Do you want the validation or the training? Okay, cool. It's basically, you can copy and paste basically most of, not that you should do that in general, but. Okay, cool. So I'm just going to run train one epoch, and then we may as well run validate one epoch as well. And so we all agree that there's going to be a host of error messages when I press enter. Yes, brilliant. Train one epoch is not defined. Oh, because I forgot to run this cell. What? Adam is not defined.
Oh, because you took it out of being
Pretty sure Adam, I didn't run this cell either, I just run all. This is why I hate Jupyter Notebooks. Okay, cool, so the training and validation loops are running. I don't actually know how long one epoch is, so I'm going to interrupt it. Assume that we only did the training loop there, and now just do the validation loop to make sure that also runs. And then let's say it's probably okay, so we can interrupt it. Okay, cool. So we've got everything working, but we're not extracting any useful information as we train and validate. So we'll revisit the loops, and then maybe we can extract, like, I guess, accuracy and loss, like we did yesterday. One thing to, so yesterday, like, when we extracted metrics, we stored them in a dictionary of lists. And I said that if you have a huge data set, you might not want to just blindly keep appending to a list that can then become huge. But the training set here has 60,000 images in it, and our batch size is 64. So the sizes of the lists, if we append to them, are going to be like on the order of 1,000. So it's going to be okay again to do it. I don't like doing it, but it's simple, so we're doing it here. So if we just add this dictionary and say we're going to have loss and accuracy, and then it's super easy to append the loss. All we have to do is what did I call it? Metrics. Oops. So we can do metrics loss dot append. And remember, we do loss dot item because we don't want a tensor and all its history. We just want the number. Everyone got that? Yeah. Sorry, up or down or? Sorry, Chris. I feel like I'm always in your way.
Yeah, but I'm not asking you not to move because you'll be someone else's way.
Yeah.
And I'm slow to that.
Hunting pack.
Yeah?
My epoch has been running for absolutely ages.
Yeah, that's probably just, sorry, so someone just asked why their training time is taking ages. It's because the data set is big and it's images. I think we might be looking at on the region of 10 minutes for a couple of epochs. So maybe like, I mean, it would be nice if we could run it and go for coffee, but we're not going to time it right. We're going to just miss it and no more. So yeah, we have a coffee break in about 7 minutes. So I quickly just want to add a function that converts between the predictions and targets and accuracy. And then once we write that, I propose we stop and get coffee. So I'm just going to add another function called getAccuracy. And like we did yesterday, we're going to protect it with the nograd decorator. Just to make a general, a general point, you can also use this like a context manager. Let's say with nograd, like do sum or whatever your calculation is. You don't have to wrap the function with it. You can use it like a context manager. I'm assuming everyone knows what a context manager is, to be honest. But actually, we'll be lazy and no, we won't.
No grad is not the same as zero grad, is it?
No, nograd basically says anytime you use a Pytorch tensor within this context, disable gradients. Zero grad deletes the history from like a calculation so that you, when you do a calculation with gradients enabled, the tensor objects remember their history so that you can then do backpropagation by differentiating all the way through. But when you're extracting accuracy, you don't want to influence the gradients because that would mess with the training of the model. And B, it's an expense, an unnecessary expense, so there's no point in doing it. So we might get in trouble here because potentially preds and targets are on the GPU. So we have to do a couple of things. So we can first of all say preds.cpu. And if they're on the CPU, they'll stay there. If they're on the GPU, they'll be moved. And we also have to turn our prediction, which is like a vector, into a decision, i.e. like a class index. So we can just say argmax, like we did before, dimension equals 1. And then, funnily enough, we're going to do the exact same thing to the targets. So this will then tell us, it'll give us a tensor, which is a Boolean object. It's true when the prediction is right for a given, go away. Why won't that go away? It's true when the prediction is right for a given object and false when the prediction is wrong. And then if we want to convert that to accuracy, all we need to do is take the mean of it, i.e. sum the number of correct items and divide by the size, which is just the mean, right? You could also do sum divided by len, but why not just, okay? Does anyone not understand what this line is doing?
Yesterday you had to call it into the upgrade.
Yeah, yesterday I was stupid. So I forgot that mean is a method of the torch tensor, and I instead imported the mean function from NumPy, and then NumPy didn't know how to interpret a Pytorch bool. When actually I didn't need to do any of that, I could have just used .mean. And that's why I was so confused, because I'm so used to not doing that I was like, what's happened? And yeah, we also need to return this, right? We don't just want to randomly issue this statement and not do anything. Okay, so we do coffee break? Yeah, no? Everyone needs coffee, so. Is that all right? No?
That's good.
No, I mean, is it all right to do coffee?
Oh, yeah. Yeah.
So in Python, actually, let's just do it as a. So
Python advises you to make constants capitalized.
Yeah, so let's just make a random Python file called test.py, and then open it. So in Python, it's considered bad practice to have naked code, which is to say you open up a file and then just start writing, like, you know, for index and range. Like, you should have all of this stuff wrapped up in functions. But if you declare a constant and then you run pylint on your code, it'll yell at you for like having a constant variable defined and like the sort of I don't know, what's the word for like the namespace? This namespace that's not inside any functions, is there a word?
It's a global.
Like the root namespace?
Global.
Yeah, so basically if you declare a variable like this, and it's a constant, you're advised to do this. But it's just it's in the Python encouraged practices, which I would be honest and say the vast majority of researchers completely ignore, which is painful to watch sometimes. Are there any more questions before we go for coffee? Yeah?
So you mentioned the
Oh, sorry.
You mentioned about the transfer learning. So how do you just do like model.weight? Is that, if you've already trained on a model, how do you pass that through instead of the weights that we were using?
So how do we use the transferred weights?
Yeah, I'm just thinking, how do you do it for your own setup? So do you train a model and you get the weights? Is that just a variable name in the model?
Yeah, so, okay, yeah, that's a good question actually. So let's grab a model and then go through the process of extracting weights, right? So if we say, Pytorch models, I'm just going to use ResNet 18, but it could literally be any Pytorch object. I don't know why my imports are taking so long, but it's starting to become really annoying. So again, f is a bad variable name, but we'll do it quickly here. So if we have our model instantiated, which is our ResNet 18, and we wanted to save those weights to file, which you obviously would be doing in common practice. Some people call it checkpointing and save the weights at the end of every epoch. So the model itself has this thing called a state dictionary, which I think you access. Oh no, I didn't mean that. So let's just print the state dictionary. So this is going to be a hideous printout, but basically it's a dictionary with all the weights and biases for all of the named layers in the model. So if we say for key, comma value, let's just say val, and f dot state dict, so we're just iterating over a dictionary, and then print the keys, it should be like, whoops, expected 2. Oh yeah, cheers. I'm so glad you're paying attention. Oh, I really, really need this coffee and you're like delaying it. No. Yeah, so like basically you can see like all of that data is there. And then the conventional way to save it in Pytorch is to use these two functions. So let's do save and load. Wait, what? I spelled load wrong, sorry. So to save the state dictionary, you just say like save the dict and then the file name. And then the extension that you're supposed to use is .pth, which to be honest, I don't know what it is, but that's what I do because everyone else does it. And then load is like just the opposite of save. Any other questions before we go?
I just want to say that in the get accuracy function, in the mean you have to specify a D type.
Yeah, so I think we had this already. So if we have two Pytorch tensors which are Boolean, and we want to turn that into an accuracy, so let's say we have, I'll just do it for like 3 element tensors, but say we have a tensor, let's do it for 2 because I can't be bothered typing out 3. So, actually I didn't mean to do that either, those are meant to be numbers. Sorry, please excuse me. So suppose we have some predictions and targets which are numerical, and one of them is right and one of them is wrong. Then if we do x equals y, we get this. So we get the zeros match, but the 1 and 2 doesn't, right? And then we want to turn that into an accuracy score. So if we do dot mean, that should give us, oh yeah, you're right. I thought that worked. Okay, so we need to do dot float, dot mean. Yeah, sorry. I'm convinced I've done this before. I don't know why. So everyone who, in your get accuracy function, immediately before dot mean, just type dot float. You probably just saved me some more embarrassing debugging, to be honest, so thank you. Okay, can we go for coffee now? Please. Before we left, someone asked about saving, you asked about saving models' weights, and I realised, I quickly mentioned there's a save and load function, but if you actually want to put the weights into the model, then you have like this load state dict function the model has. So like you just call load state dict, and then give it the dictionary as an argument. That was quite an important thing to have forgotten. Okay, where did we get to? Oh yeah, so we're in the process of extracting metrics from our training loop, and we just finished writing the accuracy function, and we had to add the dot float command that I forgot. Did everyone do that? Yeah, okay, cool. So now we'll just proceed exactly as we did yesterday and append the accuracy to the dictionary. Preds and targets. I'm really bad at not put. Yeah, sorry, no worries, hang on. Yeah, so basically this, just before the mean. So like, here it doesn't know how to take the mean because the object is Boolean, so we just turn it to a binary float. Okay, and then we're not returning anything yet, so we'll return exactly as we did yesterday. We're going to return the means, so I'm just going to import the mean function from NumPy. So from NumPy import mean. You can do it anywhere you want, but it's better to do it at the top of the cell. So then we want to return a new dictionary. What do we say we'll return? We said we'll return a dictionary which contains floats, which is wrong. It's actually a list of float, but that's embarrassing. You don't have to update this type hint, I'm just doing it. So we want to take the mean of the lists that we've populated in this metrics dictionary, right? So what we're going to do is say for key, comma, or key value for key, comma, value in metrics dot items. So this is really, so far all we've done is copied the dictionary, but we don't want to do that. We want to take the mean over the list. So we just wrap value with mean, yeah?
When we call get accuracy, is it pred rather than preds?
It is, thank you.
Can you repeat the question?
Someone just spotted a typo basically where I had written preds rather than pred. Thanks. So has everyone got those metrics? No worries. Yeah, sure. I mean, you can call them any name you want, right? But loss in accuracy seem like sensible names for loss in accuracy. Down. I mean, if I was sitting down at the desk, it wouldn't be a problem. But okay, I'm going to do the same thing to the validation loop, and we might go a little bit faster now because we done this yesterday. All we're going to do is train and plot, and Jack has some slides he wants to deliver, and I would like to not eat into that time, but I will also push to GitHub the full solution to this, so like you can finish at any time if we don't. So we're just going to do the exact same thing that we did here in our validation loop by extracting the same metrics. So I'm just going to stick this code here. And rather unhelpfully, in the validation loop, I've called the predictions preds with an S, because I'm very foolish. And we also need to define the dictionary. Sorry, so you can see it all. What is the list here? Is everyone happy with this, that I can go forward? Okay, so we noticed before that we are likely to all have wildly different training times. I don't know, I think the training time for MNIST without us being on GPUs is probably going to be on the order of like 10 minutes. I don't know for sure. But so we'll just populate this code as we did yesterday. But we may not get to run it and look at the results in as much detail as we would like. So I'm just, first of all, I'm going to create these two lists.
Have you already run it?
Yeah, just, I think you forgot to define loss.
Oh, right.
There, over there, before loss.
Oh yeah, good shout.
Yeah.
Thanks. That would probably have taken like 10 minutes to do one training epoch, and then I got an error on the first step in the validation. You know, actually one really good debugging step that you should do that we haven't done here because, well, basically because of time, is another sanity check that your model is working is to just overfit one batch. So like train on a single batch over and over again, and the loss should rapidly plummet. And if it isn't, then something's not working. So, yeah. And if you're using your own custom data set, when you, like your own, not a data set as in Pytorch data set, just any old data you work with, I usually build in functionality that lets me say, like, I only want to load 1% of my total data, so I can like quickly run the full thing before you submit your job to, like on a HPC, and then go home for the weekend and realise the error 10 minutes after you left. So we're going to append the dictionaries we created to these lists. It's really ugly that it's gone off onto another line. And then the final thing we did yesterday was these hideous lists of dictionaries can be made much prettier by turning them into a pandas data frame. So we'll do from pandas import data frame, and then we'll say so we're just going to overwrite these variables with data frames of themselves. Oops. Hello. Oh, no worries. Has anyone seen a university card that doesn't belong to them? I'm going to run this. I'll probably get errors, but let's see what happens. Okay. I don't know how long this is going to take to train, to be honest, because we are using, I am using a MacBook Air, which obviously doesn't have a GPU, so this could be, I don't know, like 10 minutes. So we don't have to actually plot the metrics because it's literally the exact same code that we used yesterday, right? You get all of your results in a data frame, and then you can visualize or interrogate that data however you like. Has anyone not got their training loop running or getting random errors? Or okay, cool. So there's two general points I wanted to make. while this is running. So when we instantiated the model up here, we end up with the really ugly non-general code because when we first import the model, the final output layer has like 1,000 classes, and then we have to overwrite it with this like manual overloading of the final linear layer. Sorry, this printout is huge. But if we change from MobileNet to ResNet or VGG, the names for the classifiers and their final layers is different. So then, like, if I change the model, I have to come and modify this line of code to say, like in ResNet, instead of saying model.classifier, you have to say model.fc. And it's like, it's really annoying and non-general. So like, one thing I do just as like a helpful tool in my own research is like I have my own code with like a model called convnet2d, and one thing I can supply to it if it ever imports. Jeez, oh. So like, if I want, for example, to compare two models, like I just have this encoder style argument. So if I want like, say I want VGG11, oops, I need to tell it, let's say we're doing 10 classes. Sorry. I'm going to say pre-trained equals false, so we don't wait in the download. But you get the idea. So like, this is the model with VGG11 style encoder. Say we want MobileNet v3 small, like we just used in the previous exercise. So you can see how you could easily just make a list of models in this way and then iterate over, like basically automate choosing a model and not having to manually go and like hack the code every time you need to change like the number of output layers. So like, I'm a big fan of making like a high level sort of wrapper model that lets you do stuff like this without manually hacking the code all the time. And another thing that I have added that I generally find super useful is yesterday when we defined our fully connected neural network, we manually defined each individual layer, which is also super ugly and non-general. So suppose like I want a model that takes 64 input features and has 10 output features, then I think, okay, cool. Actually, I quite fancy having 2 hidden layers of size 32. So then I can just say like hidden sizes equals, now the model has 2 new linear layers in the middle. Then suppose I say like, actually I quite fancy applying dropout to the input specifically. So then I can say input dropout equals 0.1, let's say. So now, let's do that again. Now it's added like a dropout layer to the start. And then again, the same thing, like if I want to do batch normalization to the input, I just add this. Oh, sorry, so now you can see it's got batch norm and dropout. So like, I think if you work in like a research group or in some kind of organization, I think everyone who's doing any deep learning related stuff would benefit massively from making like general shared objects like this that everyone uses rather than you manually instantiating models, and then you massively reduce your code duplication. Like this looks a lot cooler and more professional than like the printout we had yesterday of the model, which was really ugly. And once you make these tools, they save you tons of time, and it's really, really easy to change the architecture and look at the performance, and then like, you know, basically build a model in like a general way rather than saying, okay, what happens if I add another linear layer and then going and manually copying and pasting a new linear layer? It's just like, it's super bad software engineering, to be honest. Or it's not software engineering.
Is there somewhere you can get that code?
Oh yeah. I don't want to punt my own repo, but Jack is pushing me to do it. So I have a bunch of models in a GitHub repository called Torch Tools, which I basically use in my own research. Am I signed into GitHub? Yeah. So like it has a bunch of like literally ready to use models, and you can ask for pre-trained weights and it downloads them automatically from Pytorch. So like I have FCNet and ConvNet were the 2 things I just showed you. I also have a unit, some autoencoders and stuff like that. But yeah, like if you want to just use, for example, the simple FCNet model, it has documentation. You can install the repo using pip. It's tested. Yeah, Simon.
What's the license to that, Jim?
MIT.
Thank you, Jim.
Is that okay? I mean, I'm not saying you should use it, but like you should, if you're in like a research group, I think you should make something like that or use an existing code that's good. Don't like have all these random Python files with like half-baked models, and then you just have a super big mess of unmaintainable code. Yeah, apparently good software and research is a thing we care about. Yeah. So yeah, this is going to keep training for I don't know how long. So I think we can basically stop here and Jack can take over and do his final part.
Where were optimized with loss func defined?
Oh, sorry. Here. It's the same ones we used yesterday, if you by chance remember. I would also, just quickly, now that we're here, look at the documentation for the loss function because there are other parameters you can modify. So there's like, for example, a thing called weight decay, it adds like a L2 regularization penalty on all the parameters. So it penalizes their size. So you can say like, I want to include in my loss some sort of penalty that stops parameters getting too big, and that can potentially lead to you not overfitting. So there's like a whole bunch of things you can tune that we won't be able to cover here, so it is important to read. Yeah. Can we pass the microphone to here, whoever's got it? Who's got the mic?
I guess there's so many options here, right?
Yeah.
That you can put in them. I mean, if you get different results, quite different results from just changing some of these smaller parameters, should you really believe the training that you're getting and the model that you produce at the end? I mean, surely it should be fairly robust to some of these.
I think in some ways, if you change like the learning rate and the weight decays by reasonable amounts and then your performance suddenly dies, then it's a sign that maybe your data set's too small, maybe you don't actually have a really good model. But like a model is only as good as it's tested. So the main thing is like if you have a deep learning model you want to deploy on a given application, then you have to test it on truly independent unseen data. That means not validation, right? Because there's information leakage. You learn from the validation set by choosing when to stop training. So you basically need like really strong scientific objectivity and a good deal of paranoia, to be honest, because like if, for example, my previous job was in medical image analysis, so like the use case is much more serious than classifying like handwritten digits. Yeah, okay. Yeah. So I just unplug. Clean this stuff up. Cool. Oh, sorry.
So you know you've got the like two device thing
Mm-hmm.
to choose whether it's run on the GPU or CPU. Would you use that with num-workers, or does that kind of replace num-workers?
So num-workers specifically refers to, so the data loader object will like serially load mini batches one at a time. But if you say num-workers, then it will spawn CPU processes which independently load separate batches. So the devices, basically it doesn't replace num-workers. Num-workers specifically refers to how many workers the CPU will use to load data from disk.
Cool. So I've got some slides now on actually applying machine learning within the climate science setting. And I will talk, but I am by no means an expert on everything that's in here. So if people have things they would like to contribute or comment, please do just stick a hand up and shout out. So to sort of summarize what Jim's done for 5 hours, into one slide, we've learned that we can do, there's two types of things we can use neural networks for. There is classification and regression that we've been through, and we do these by using either ANNs for kind of this tabular data or CNNs for image-like data. So one thing I think that becomes quite important within the climate science is recognizing what image-like data is. So all these classic things we sort of learn about and train on are images, cats, dogs, numbers. But when a neural net sort of works on things, so this is one of the digits from the MNIST set, and some people have sort of tried to, when I talked about feature recognition earlier, tried to understand a little bit how these kind of encoder layers are working. So if this is a digit here, what you might get is the encoder is sort of picking up or matching features like this. So a red gap, so a gap in the image in the center and sort of some kind of circular lines around the edge. And then when you pass that over your image, it's picking out the zero like that. But if we think about climate data, a lot of what we have can also be viewed as an image of sorts. So here we've got something, gravity waves, I don't know what they're plotting, temperature maybe? Anyway, but you can see, you could take this data, which is, it's temperature, its physical variables, but you could pass this into a convolutional neural net and start looking to trying to train to maybe pick out either wavelengths or sort of the length of the gravity wave or how long it's lasting for, that sort of thing. So convolutional neural nets are what we very often apply in climate data. So potential applications in geoscience. So there's a really, really good review paper basically on this that I would suggest taking a look at some point, and these are linked from in here. But sort of the key uses we have are emulation of existing parameterizations. So sort of taking something that's very computationally expensive, physics-based, and learning how to do it with a neural net, hopefully faster. There's also data-driven parameterizations, which is where we say we've got physics-based models that inevitably ignore some physics. Maybe if we have sufficient data, if we train directly on the data, we can actually capture that missing physics. We don't know how we're doing it, but we do. Downscaling, upsampling, I think there are some posters on, but this is sort of taking coarse data and trying to infer finer resolution. Time series forecasting, hopefully everyone's happy with what time series forecasting is. Equation discovery, so I don't know too much about this, but I know there is a ICCS project, but this is, say, if you've got subgrid models, so you might have a turbulence model and you need to apply subgrid closures, you might give a model sort of a number of plausible different options for those closures and actually use the machine learning to decide what form you want that to take. And finally, there's complete forecasting, which I'll come on to. So yeah, parameterizations. Our models are full of parameterizations. So classic ones being kind of cloud microphysics. We aren't going to be modeling individual raindrops, particles, aerosols within a climate model. So we have to kind of represent this in a bulk fashion some way. And typically, these come out as being quite expensive parts of running climate models. So microphysics, I say, and also radiation, radiative transfer are two of the kind of the big offenders that eat up a lot of time in these models. So the main idea of this is that if we can go offline, spend a lot of time just doing a big parameter sweep over our parameterization code, we can map out sort of enough of the space, train a neural net, and then the neural net can fill in the gaps of any inputs we then give it down the line. So there's an example of this for gravity waves in this paper here. Yeah, the idea here is speeding up and reducing computational time. There's also, I mentioned, the data-driven parameterizations. So here, like I say, you're inevitably always missing some physics from any physical model you write. Not entirely true, but if, say, if you have data that has all of that information in, perhaps even if you don't know exactly how it's working, you can get a better representation, build more accurate models. So this one's more dealing with trying to improve accuracy. And then the final one, where there's quite an interesting idea here, is, so I said, you've got, say, models of, you're representing your cloud physics, your rain, your sublimation, all of that, with some kind of bulked parameterization, but you do get cloud resolving models that will run. The only thing is they're at a much, much finer resolution. So if your climate model is running on 60-kilometer boxes, there's a lot of clouds in 60 kilometers. If you want to model the individual clouds, you need meter boxes, which obviously we can't do in the climate models, but what some people are doing now is running these much higher resolution models, again, in a bit of a parameter sweep, and then training subgrid models on those high resolution models. The idea hopefully being that you can kind of get the benefits of running the subgrid model without the expense of doing so every time. So yeah, downscaling. So this is trying to get information for free, and free in inverted commas because nothing is ever free. The expense you pay is when you do your training. But the idea is if you've got kind of a nice data set that you've run on high resolution, giving you very accurate information, can you take a much coarser model and kind of based on the coarser model infer the information down there. So suppose we wanted to know where it was going to rain. If we say it's going to rain in a 60-kilometer box, that's not so useful, but if we can kind of learn how to downsample onto something like this, you might be able to provide more reliable, more accurate forecasts. And so one of the things you might want to consider as an input here is topography. And I know there's some people with posters, so we can have a look at that maybe over a posters this evening. Posters today? Yeah, okay. Forecasting, so time series forecasting is feeding something a time series, trying to predict things out. So if I have information in about sort of wind speeds and humidity, can I predict what the temperature is going to be or something else? And for these, we haven't covered these today, but often recurrent neural nets are made use of. So these are neural nets that have things built in that can consider time history rather than just instantaneous input to output mappings. So that might be something you want to go and look at for that. And finally, we have complete weather forecasting. I will let you sort of form your own opinions about this. So this is where rather than replacing individual bits of a model, the big players, so NVIDIA, DeepMind, Huawei, have basically built end-to-end, I'm going to do forecasting everything with a neural net. So the way these are done is they train them on the Error 5 dataset. So those who don't do so much atmospheric science, this is ECMWF, who are a forecasting group, have a big climate model, physics-based, and they run this model to generate you a weather forecast. After that has happened, and we've got observations of that time period, what they do is they take those observations and feed them back into the model and run the model again to try and get a sort of a more accurate estimation of what did happen. And you can then fill out all the gaps in between where you don't have observations with the model results. And so this gives us a really, really nice data set that has sort of regularly gridded atmospheric data and information across the whole globe at quite a high time resolution. So this is the output of a physical model at ECMWF. These neural nets have then been trained on this data. And so if you look at a lot of the papers, this one I think is Pangu Weather, and they sort of point out and say, this is great, we can beat ECMWF. And what they're saying is they can beat the predictive capabilities of ECMWF, but they've actually trained on ECMWF with the data assimilation. So yeah, it's an interesting claim. One of the downsides, of course, is that by running these models, you don't have any physical insight. So these are great if you're coming from the operations end of things. You want to run forecasts quickly. They are hugely quicker. Again, nothing is ever free. So I think I was at a meeting recently and they said it's that. So ForecastNet, I think they quoted, was trained on order of 400, 500 GPUs for 40 days straight, which is, yeah, it's quite a lot of flops. And I can heat a lot of swimming pools with that. But then when you run it in inference, it's much, much quicker. And this is their classic plot. And I would like a particular bugbear that I think, if we're going to be better climate scientists in this community, papers are full of, here's my hugely complicated image showing stuff, and here's what my neural net made. Don't they look similar? And you can tell very little from this, really. It's like, yes, there's red in the middle, there's blue at the tops, but really what we should be doing is constructing some kind of actual numerical metrics by which we can write in papers and say whether they're good or not, because you could easily manipulate this to show what you want just by choosing sort of convenient color maps and convenient slices. So whilst it's nice to demonstrate a point, more papers, I think, should be looking at backing these sorts of results up with proper metrics. Yeah?
Also, to go slightly beyond numerical metrics, you can also say, does my model respect known physics? Does it like mass go negative and stuff like that?
We'll come on to that. So those are some of the applications, and I'm sure some people here are working on some of those. So then I think some of the challenges, so this is where I think the bit of your job that ChatGPT is not going to take is actually, as Jim was saying he was teaching, being sensible about things, thinking critically, and making sure we're doing things in a sensible manner, sensible for our data set, sensible for our applications. So someone asked a really good question, I think it was yesterday, about cyclic data. So one important thing to think about is how you should prepare your training data. And we saw a lot of that with the penguins data set, making sure that we have things that are sort of always the same magnitude, how to encode strings, this sort of thing. But yeah, I can't remember who it was who asked about diurnal cycle data. So if you have something that's, say, hourly wind speeds, these are going to change with the diurnal cycle and possibly with other cycles as well. So you're going to have seasonal cycles, annual cycles. So you need to think...
As well as quasi ones as well, right?
Or even quasi-biennial ones. So you need to think, how do you deal with this? You can't just chuck information blindly into your neural net. So the obvious one might be to use time as an input. That might work in your instance. Maybe it doesn't. Maybe you don't have time data associated with this. So alternatively, maybe if you're looking at daily data or something that has a diurnal cycle, can you use a daily average instead? Is that sufficient for your application? Is it going to give you sort of reliable results? So again, training data. So another one I think that doesn't get talked about much is training in a changing climate. So if you're training, say, a sea ice model and you have 20 years of data of Arctic sea ice extent, do you train on the first 17 and then validate on the last 3? What do you say about the applicability of your model? Because it's well known. So this is the famous doomsday clock from NASA? Yes, NASA, of how since the 80s, global temperature has been spiraling out towards that 1.5 degree limit. And we know that sea ice extent has got less and less every year. So if you're going to train a model to predict sea ice extent on something that's got a time basis that's changing, how can you say that's going to accurately predict sea ice extent in 5 years' time, 10 years' time? Because at some point it's going to be 0, right?
Sometimes people call that domain drift.
Yeah, okay. So yeah, I don't know if Jim's picked up or not, but that's called domain drift, sometimes. At the same time, if you've... where's it going to go? So this also ties into preparing your training data again. So rather than splitting with a train on 17 years, validate on 3, maybe you want to be sort of picking from interspersed intervals instead. Again, so previously I did some work in space weather. So this is where you get sort of quite high fluctuations from the sun, so energetic particles that come through, and there's a big worry that if you get hit with a particularly strong coronal mass ejection, it's going to knock out power systems, banking systems, electronics. And there was, I think in the 80s, there was a storm that did take out a lot of the power grid in Canada. But these are quite rare, so we call, often in geosciences, we call these the 1 in 100 year or 1 in 1,000 year event. Similar ones we've seen, I think, recently are flooding or storm surge, this sort of thing. And if you've got training data from the last 50 years, this might be great for kind of day to day, but what's it going to tell you about extreme events? So this is, yeah, again, something else to be aware of when you're going through. Also, does anyone have any comments or questions? No? Okay. So then I've got some stuff about physics-informed approaches. So as Jim showed us, particularly with the end-at-torch tools, there's a huge variety of ways that you can build neural net, the different layers you have, the different ways you're treating, whether you sort of bottleneck your data, whether you expand your data. And it's sensible to choose one that's appropriate for your application. So yeah, don't go in blind with your machine learning hammer and slap your 5-layer convolutional neural net like some research groups might do. Have a think about what's going to be the most suitable and the most applicable to your particular application. So there's a really nice example in this paper here, which is, so they're looking at radiative transfer. So this is how energy, solar energy comes down, or heat energy comes down through the atmosphere, reflected by clouds and Earth's surface, and sort of comes back up. Could anyone think of why it might be a problem to use a fully connected net for this? So your inputs are, say, temperatures at different pressure levels throughout the height of the atmosphere.
Well, you end up drawing connections that aren't there physically because there's no information flow.
Yeah, so you're just feeding data into a net. It's quite possible that the net is going to learn or is going to spot spurious correlations between, say, the bottom of the atmosphere and the top of the atmosphere that we know physically can't be there in reality because information, heat, has to propagate down through the atmosphere, and then back up. So there's, yeah, this paper's quite nice. So they use a recurrent neural network here, which then allows you to restrict the information flow going in either from top to bottom or bottom to top. Yeah, Tom. Yeah.
Just in that example, though, it's interesting because actually you can think of a way in which the top of the atmosphere and the bottom are correlated, right? So if you have a low temperature at the bottom of the atmosphere, low temperature at the top, then there's less gradient. So maybe, like, perhaps, maybe it's consistent.
But not on the time scales of...
So the point is that at that instantaneous time, the information needs to travel at the speed of, can't travel faster than the speed of light, so it can't be instantaneous. But if you're looking at, you know, what could happen over time, at some point later, or if you knew, you know, in the morning the temperature's the same at these points, then actually it might make sense to draw a connection between them, because perhaps that means there's not going to be as much wind flow or, like, you know, turbulence or something. So it's a kind of, these things require a lot of deep thought.
Yes, yeah.
Yeah.
Yeah, and so I should say this particular example is radiative transfer. They were trying to replace a parameterization, so they were looking to do it on quite short time scales, as in short model time scales. And having a recurrent net means actually they do also bake in some time history to that. So physical compatibility is also important. So a lot of what I've called, and hopefully I won't upset Jim, classical machine learning applications is where we have something that does machine learning end-to-end. So think about ForecastNet or medical image recognition. We feed it the image and we get out, have you got cancer or not? Often what we're doing is replacing bits of much larger models. And so there's a number of considerations to go into here. The first one I would say is that you could spend hours and hours perfecting a model offline. So you generate the output, say you take your cloud parameterization, do a huge parameter sweep, that's costly in itself, generating all of these training data. You then run all this training data that could be very expensive. You're getting a model that's doing sort of 80, 90% accuracy, fantastic. Slap it back in your model, and you'll find the whole thing crashes, and you've spent a long time finding a way to crash your model. So this is, offline models are not necessarily going to be stable online, and this is because even though you're emulating a parameterization, you're still going to have, you're not going to perfectly reproduce it. There's going to be slight numerical errors in there. If you then put these in, much like you would with classical methods, some of these errors could be unstable modes and then grow within the model, generating waves, high gradients and breaking. So this is not necessarily a new problem to physical modeling, but it's something to be aware of. And I think this is where a move towards online training is likely to grow. So this is where you train your model whilst running your larger model at the same time. But again, you've then got the overheads of the rest of the climate model rather than just the parameterization. The next one, so this hasn't formatted correctly, but anyway, is if you say you've trained a neural net for forecasting water content or cloud water or rain, neural nets are stupid. It will be perfectly happy for some conceivable set of parameters for your neural net to chuck out negative rain, because we fit a function. And if you pass it something that moves into below zero, that's what it'll give you. So even if you apply sort of heavy penalties, this is not necessarily going to fix that. It's still a possibility. So you need to sort of exercise some common sense here. Again, this isn't a new problem in parameterizations. So even with physical parameterizations, there's been cases where you need to enforce some kind of physical compatibility or physical constraints. And a bit like Jim mentioned earlier, these might be things also like ensuring you're satisfying conservation of energy or conservation of mass. But yeah, if you're writing these things, have a think about it. Redeployability, so a lot of what these things are doing, so say you're working in cloud physics, if you take the sort of the very famous Thompson model, the Thompson model is just a set of equations in a paper 2011, I think, and lots of people have written this model up for many, many different numerical climate atmosphere models. So it's a microphysics model from one paper that's been redeployed in many, many other locations. Can you do that with your machine learning model? So what exactly has it learned? What was the training data you gave it? It may be that if you've, so I'll start with this one first. If you've trained on the output of a parameterization and one of the things you gave your model was the pressure level height of your model, then it's always going to need those pressure levels to be inputs. So if you now want to take this and double the resolution, or move it to something that's an irregular grid spacing, this isn't as simple as just redeploying physical equations because you don't know how the model is using those specific pressure levels, so it's going to be much harder to redeploy. Similarly, if you move from, say, so the example I talked about earlier with emulating subgrid models, if you've got something that's trained on a subgrid model using meters of height, and then you want to then go and redeploy it in something that's using pressure as the vertical coordinate, how do you do that conversion? Maybe if it's on a local scale, you can use some kind of hydrostatic balance, but if you're moving sort of out to the atmosphere, there is no hydrostatic balance that covers the entire globe. So how do you handle that? Well, can you handle that? And similarly, if you've trained on a particular geographical location, how relevant is that to the rest of the atmosphere? So there was a talk I saw last week where they'd trained, I think it was heat wave predictions from data in Peru, and then they were trying to apply this out to countries across the globe, and you sort of say, well, Peru, the cities are all down the coast next to a range of mountains. This has a sort of significant implications, and it's next to where you get your El Nino, La Nina events. All of these are going to feed in. You can't just take that model from there and slap it onto Morocco or Sicily, which they were trying to do. So finally, I'm going to spend just 10 minutes. I know some of you have been eagerly waiting, shilling some of the work that we've been doing in ICCS on the problem of interfacing. So this final challenge is that is focusing on when we're trying to replace kind of some physics-based components in larger models. So radiative transfer, microphysics, turbulence closures. And as we've seen, there's a lot of very nice machine learning frameworks that are typically written in Python, so TensorFlow and Pytorch. But the vast majority of our big models are written in some other sort of higher level language for reasons of sort of speed and efficiency. So the Met Office at the UM, the IFS at ECMWF, ICON with DWD, WRF, SESM, these are all Fortran-based models. And so we've now got the problem of how do we connect all of this stuff we've written in Python with something in Fortran. And this is not a trivial problem for many people, especially sort of domain scientists specializing elsewhere. So I would say what we really want is we want something to bridge this gap that's not generating sort of additional work or additional training time for the user. So you don't need a deep understanding of computer hardware, what's happening down sort of below the language. You don't want to add excess dependencies to your project if you can. A lot of these models are sort of national systems, quite tightly governed. You want something that's going to be easy to maintain, and you want it ideally as well to maximize any performance. So your neural net might be 5 times faster than the parameterization you're trying to replace. But if the process of data transfer and copying things from the model out to the net and back in takes 10 times longer than the parameterization, then it's no use, right? So there's a few options out there. I know some people this week have talked about 4Pi and SmartSim. The one thing I think we would all implore you not to do is to write your neural net in Fortran. So Jim did tell us how we can save the weights from our Python neural nets. You could conceivably then read these into Fortran, build a neural net. Please don't. You're generating a lot of extra work for yourself. You're generating the problem, as Jim pointed out, that you're going to have to write all of this and deal with that. It's not going to be sort of replicable, and there's a good chance that you're going to do it wrong. Remember that Python has a different memory structure, so you're going to have to think carefully about flipping your matrices and arranging your weights in the correct way. And people, I think, who owns Pytorch? Is it Google? It's Facebook. But yeah, Facebook have put huge amounts of time and effort into making Torch extremely feature-rich and efficient, and any code that you're knocking up in Fortran is probably not going to be as good. So this is the typical way of running things. So you have your Fortran code up here. You've got some data that you passed the parameterization. That has to go out to the Python runtime. And this Python runtime is situated in a Python environment. And it will then run PyTorch or TensorFlow. Additional issues you've got here are that you now have to manage your Python runtime alongside this. So you need to make sure that you've got the right virtual environment, make sure that you've booted that virtual environment up, make sure that you've got properly connected libraries and managed all of this carefully, and do it on a HPC. And so notoriously, I think, So our alternative approach is to actually just bypass Python entirely. So PyTorch and TensorFlow are both written, as we heard, in higher level languages underneath, so C or C++. Low level languages, thank you. I suppose. And so actually what we are going to do is go past the Python and just go directly to these efficient languages instead. And this is particularly good because I think XKCD sums up quite well that Python environments, and indeed some of the ones we've seen this week, yesterday, trying to set up, can be an absolute cesspit and break. So we've produced 2 libraries that you can use to do this. Like I said, we use the C bindings to access straight out to the lower level languages rather than going through Python. There's a performance benefit here because this avoids Python runtime, which is typically quite slow. And we're also implementing a no copy transfer, so we don't have to, provided we're staying on the same device, we don't have to copy tensors or data out to memory in order to read it in again. The ease of use aspect, so there's 2 types of efficiency. There's the efficiency of the neural net on the computer, but there's also efficiency of the person writing the code, spending time developing the code. And so to sort of aid with this, we've got quite a nice, pleasant API that I'll go through shortly, and a number of utilities to support developers with implementing this. And a number of examples. So this is an example, and I should say this is developed with Simon, who sat at the back, did a lot of work on this, particularly the TensorFlow side, and Athena, who is now at NVIDIA. So we take the model, this is assuming you've got a model file that's been saved somewhere. So like Jim showed us with defining the various different layers of our net, and we've trained it. You can now save this as Torch script. So this is something that saves both the model structure and the weights to a file that can then be read and interpreted by other things. So you do this with, assuming you've got a trained model, you initialize it, which is sort of the process of loading those saved weights in. You then run this function that's already within Torch. So this is already in Torch. Torch JIT script saves the model or converts the module to Torch script, and then you just save it like you would sort of anything else in Python out as a torchscript.pt. So then once you get there in the Fortran, you need the C bindings, which come within Fortran, so they're already there. And you also need this is the library that we've written that will allow you to couple the two. And the process of loading a Pytorch model in Fortran is as simple as just calling that saved Torch script file here. It's exactly as you would do if you were running it in Python, almost. Creating tensors is a little bit more involved. So suppose we have something like sea surface temperature here. So this is a Fortran array of reals. So this is data that's in a model, and output is whatever we're wanting to get back. We need to create some things to store the data and give it to Torch. And for this, we've created these types, Torch tensor here. So as long as you declare these, what you can do is then pass the relevant parameters. So you need to give them the shape and the dimension of the arrays. But you can then call this function Torch tensor from blob, which will map the SST onto this input array here. And you do the similar thing, mapping your output Fortran item can be mapped to the tensor item model output there. Then running the model, you just call the function torch module forward with the name of your model that you imported back here, the inputs, the outputs, and the number. And it will go away, run your model in C or C++, and return you the answer. And then at the end, all you have to do is make sure you clean up to keep everything from memory leaks. So that's all I've got to say. There's some references here. The slides will be online. I'll upload them hopefully over lunch. But the HTML and the source for all this is on GitHub. If there's any more information you want, you can contact myself or Jim. Are you happy people to? So our contact details are up there. And there's also, if you want help with something on here, get in touch with the ICCS. And I will be doing one of the items in the hackathon. Will be looking at profiling and developing some more functionalities for the Pytorch library here. So if you're interested in learning more, join our team, I guess.
And we will push work solutions, cleaned up work solutions to all the exercises.
Yeah, we'll put the work solutions, cleaned up solutions onto the GitHub repo. So once they're up there, we'll send an email or a Slack message, and you can just do a pull to update your repository. Are there any questions, comments, things people want to say?
Did you mention that you also have a TensorFlow coupling for Fortran?
Yes, we've got TensorFlow coupling as well. Our general advice, based on kind of looking at the runtimes and the ease of use, would be that if you're starting a new project, use Pytorch. It's much easier to develop in, and it's much easier to connect and faster.
Great, let's thank Jack and Jim again.